Today we are going to do section 3.2, okay, on page 205, where we have the domain and range. The domain is all the stuff that you can put into the function, and the range is all the stuff that the function might become. That is, for example, let's look at the graph on the page. We have the domain here, okay? We have a collection of stuff, right? And everything that's in the collection that can fit into the function is called the domain. And the range is everything that might get spit out, okay? Every possible conclusion that comes out of it. So as an example then, let's look at the next page, 206. But before we look at an example, let's review some of the notations here. The notation is there are different ways of saying the same thing in explaining ranges. Is what you might wonder, why do we need all these different ways of saying things? Well, it's just a tradition, okay? We say things more than one way. So, for example, let's look at the chart on page 206. And let's say you have first one. If you have x is bigger than a, what's a? Well, let's say a is 2. Okay, x is bigger than 2. What does that mean? That means all numbers that are bigger than 2. Doesn't matter what it is. As long as bigger than 2, it is what we're talking about. And in notation, one way you can say that, of course, is where a goes from, where your set is described as going from a to infinity. Now, the parentheses means that a itself is not included, okay? A is not invited to the party because x has to be strictly bigger than a, and a is not bigger than a itself. So a is not included. However, anything bigger than a, no matter how little, that is bigger, okay, and it's still included in the set. So that is the one notation. The next one is you can graph it from a and all the way to infinity with an arrow indicating that we're going that way forever. Now, to show that a is not included, the book very carefully the blue line very carefully doesn't touch a, but the more common notation in my day is you just draw a circle here to indicate that the a is not included. Here's a, okay, and then we'll draw a line that goes in that direction. That is often how it's done. But either way, the arrow means it doesn't stop. It'll go forever all the way towards infinity. So that is how we express it, and then we even have a description here. That just means x is greater than a. Well, that's how you say this, okay, in word form. Now, the smaller than a is the same principle. It just goes in the other direction, okay. And the next one, we look at x is bigger than or equal to a. The only difference is the endpoint is included, and we signify that fact by using the bracket instead of the parentheses. So that the only difference is a itself is invited to the party, okay? A itself is included. And similarly for x less than a or equal to a, same principle. We go the other direction, but a itself is included by the fact that we use the bracket instead of the parentheses. Next, let's look at the next one where x is between a and b, or this is x is bigger than a and less than b. Okay, and then because it doesn't include a and b, we use parentheses that goes from a to b, and similarly on the number line. That just means that the endpoints are not included, but everything in between, no matter how close to a and b, as long as it's bigger than a and less than b, then it is included, okay? Even if it's it's only a very tiny little bit bigger than a. And say if x is only, let's say a is 2, and x is actually only 2.0000001, that is still included because it's still bigger than a. So we're going full technicality here. As long as x then is bigger than a and less than b, no matter by how little, okay, we still count. So that's that. And next, we have a mixed situation where x is bigger than or equal to a, but less than b, which is fine. So the side where we have the equal sign included, then we use the bracket. The side that doesn't have the equal sign included, we use the parentheses. And the same way if the situation is reversed. Or if both sides have equal signs, then we use brackets on both sides. And that's the last situation. So having said that, let's consider example 1. What does it say? We need to find the domain of this order pairs. An order pair is any two numbers that's in parentheses. That's different. Okay, that's different. We just said a little while ago that that also means x between a and b, right? But that is different. Even though they look the same, right now an order pair means something completely different. So do not confuse the two. All right. And how do we know one's an order pair? Because it said so. And anyway, so right now, the 2, 10 is just in the first one order pair is just an order pair. Okay. And so then what that means is that it describes a function such that if the input is 2, then the output will be 10, period. That's all it says, nothing more, okay? And then the next one, the order pair, is 3, 10, 4, 20, etc. Now, so this function is only defined for 5 items, as far as we know right now, okay? The 5 items being 2, 3, 4, 5, 6. And each of these 5 items will be sent to whatever 2 goes to 10, 5 goes to 30, 6 goes to 40, etc. And you might wonder, what does the function do to other stuff? We don't know, and we don't care. Right now, we only care about the function is only defined for these 5 inputs, and that's all we care about. So what is the domain of the function? The domain then is 2, 3, 4, 5, 10. That's the domain. That's the entire domain, 5 numbers, okay? And then the range is where does the function go? The range in this case will be 10, 10, which is just 10, 20, 30, 40. So the range is 10, 20, 30, 40. So that is the domain and range of example 1. It doesn't ask for the range right now, but that's the idea, okay? So the domain is where the function the input is, and the range is what all the possible output can be. So that's example 1, okay? Please do that as part of your homework. As you can see, it's a very short problem, all right? And let's move on to example 2. Now there's the domain of x squared minus 1. And what can you put into a function called x squared minus 1? Well, you can square anything, right? Negative, positive, whatever. So then the domain is the entire real line, or also called all numbers, all real numbers, or you can write it as from negative infinity to infinity, as the book indicates. Okay. Now remember the symbol 8 lying on the side means infinity. Why? I don't remember. But that's the way it is, okay? So that means from minus infinity to infinity just means all numbers, okay? Any number you can think of. But it does not include infinity though, because infinity is not a number. So next, let's look at the example 3. Well, please do example 2 as well as part of your homework. And in fact, do all the examples as part of your homework. And so example 3, we have domain of a function that involves a denominator. Now, the only time that matters is that we have to be worried about the denominator cannot be 0. Therefore, when you look at this function, it has 2 minus x at the bottom, right? And that 2 minus x had better not be 0, okay? It is not allowed to be 0. See the 2 minus x? As long as it's not 0, then everything is good. So if 2 minus x cannot be 0, that means x cannot be 2. So the domain is all real numbers except 2. Okay, so then let's look at the answer. And so the answer is given in this form. Okay, see, now the book draws a circle where I said people normally draw circles. See, the book is drawing a circle right on 2. The circle means there's a hole there. And the hole looks pretty big, right, so that you can see it. But the hole actually only includes the number 2 and nothing else. not 1.99999, not 2.0000001. Okay, for as long as saying 0 as you can stand it, it does not include those numbers because those numbers are not 2. The circle only includes 2 in it, so the hole is a very small hole. Okay, so then in that notation we can write it as, so the domain then is anything time x is less than 2 or x is bigger than 2, also written like this. Now that U-shaped thing is pronounced union. Okay, so this is, you can also call the domain goes from -infinity to 2, union to 2 to infinity. Or there is yet another way of saying this. Okay, the third way of saying this, you can just say x not equal to 2, and that's perfectly acceptable and perfect. And personally, I think that's the best way because it's shortest. Okay, I mean, what's the domain? X is not 2. That's all. Everything else is good. And so that is example 3. Please do that. It won't take you long, I don't think. So example 4, we have a function with the square root. Now the square root has, for real numbers, when we did complex numbers at one point, but we're not gonna ignore that, okay? And we're gonna go back to just real numbers. Now for just real numbers, you cannot take square root of anything that's less than 0. And then so as a result, that thing in the square root, 7 minus x, had better not be less than 0. Okay, so the 7 minus x has to be bigger than 0. Okay, and then so you solve the inequality. So 7 minus x has to be bigger than 0, which means that minus x has to be bigger than -7. So you divide the -1 out, and remember, whenever you divide or multiply a negative value in inequalities, you have to flip the inequality sign to the other way. Or put it another way is that you need to move the x to this side, okay? It becomes positive, and move the -7 to the other side. So then it becomes, if you did that move without flipping the sign, this will be x, and that will be, it will read 7 bigger than x, right? Which is what this says, 7 bigger than or equal to x. So that is the same thing. So please do that example 4 also as part of your homework. Okay, now next page. Now we are on page 209. We are doing, what is that? Okay, we're describing some notations again. 209, all right. And it doesn't hurt to remind you to all these notations, what they mean, because sometimes you forget it and then you look at it and don't know what it says and think it says something really, really hard to understand, and it doesn't, okay? It just says something like numbers between. Okay, the first one, let's say is h is bigger than 5, but less than or equal to 10. So the bigger than, you draw a hole there, okay? The less than equal to at 10, you draw a solid thing. Okay, no hole, which means it includes 10, but does not include 5, and is in between these things. So you can do the inequality notation or the set notation. The set notation reads as the set of all h such that 5 is less than h less than equal to 10. That's how you read it. Or you can use the interval notation, which is use the parentheses 5 bracket 10. That is parentheses 5 comma bracket 10. All that says the same thing, okay? And you might see something like that often shown. Although for this situation, I would say that most commonly you will see the first one, the inequality notation, because it's the most, the shortest and simplest way of saying things. But you should remember what the other stuff mean. You know, this is kind of a math language class. So when you see the bracelets and all that stuff, this thing right here, okay? And when you see that thing, do not be confused like, whoa, what is that? I've never seen that before. Yes, you have. That just means that. That's it. All right, so remembering that, now the next thing is very similar. We just flipped stuff around. Now the bracket is on the over 5, okay? And whereas the circle, the hole, is at 10. But otherwise, it's the same. You just arrange things accordingly. Bracket goes over where it includes 5. Brace the circle, which means the parentheses, means when it doesn't include 5. So that is the situation, the second situation. Third one, h is, and both sides are wholes, okay? We do not include 5 or 10. Then the next situation, we have everything is less than 10. So we just keep going. We don't even care about 5 anymore. So we go backwards from 10, not including, all the way back to negative infinity. And that can be written as just h less than 10, or the set of all h such that h less than 10, or parentheses negative infinity, comma 10. Okay, close parentheses, being that 10 is not included. And then another possibility is if h is bigger than the next one, what if h is bigger than n or equal to 10, then we include 10, so there's a solid dot there, or in the set notation reads as set of all h such that h is larger than or equal to 10 right here. Okay, that's the set notation. Or you can draw the last one, 10, bracket 10, comma, positive infinity. Positive infinity, you don't need to write the positive sign there, but you do need the parentheses to mean that the infinity is not included, because we can't include infinity, okay? We can't do anything to it, really. So then eventually, of course, the last set is called all real numbers, which can be written as and you just say it's all real numbers. You can't use the bigger than or less than sign anymore. Anyway, so, or you use the parentheses, which goes from negative infinity to infinity. And sometimes I also use this thing right here. Okay, this is done sometimes. So you might as well see it now to get it, to start recognizing. When you see the letter R printed like this, the most of the time it means all real numbers. There are exceptions to that. I've seen the book do use R just mean average R, that means nothing, which I don't think they should do that. That specific way of drawing R, the capital R, should be only used in math anyway. This symbol should only mean the entire real number line or the x-axis. Okay, so but anyway, that's not that big a deal right now. I just want you to sort of get an impression of that in your brain, and we'll look at it some other day. Okay, and so that is that should be that. Okay, let's go to the next page, and we will look at the next example, example 5. What are we doing here? Example 5, we want writing stuff in set notation or whatever other notation. So let's look at the graph of stuff. And we have something that goes from 1 to 3. Okay, look at the graph. On what page am I on? And maybe I should write that down first. We're on page 210. Where we have a set notation matter. Okay, let's look at the graph on example 5 of 210, where we have this thing right here. Okay, now take a look at this thing. We have, okay, so the value of x, you can see it goes from 1 to 3, inclusive of both ends, and then 5 onward, not including 5. So we're going to say it like that, like it says. See, x goes from 1 to 3, including 1 and 3 with an equal sign, or x bigger than 5 doesn't include 5, no equal sign. That's it. Another way of saying it is the same as this, except you draw a bracelet around it and write down x and write down the vertical line. So this thing reads as the set of all x such that 1 is less than x less than 3, or x is bigger than 5. Okay, that's what that sentence says. It's not that important if you know how to read it, just know what it means. So and finally, the interval notation, of course, it says that it is bracket 1 to 3, means including both ends, and then the union, okay, that's the U-shaped thing, and then the other one says parentheses 5 to infinity, comma infinity, close parentheses. Just that means 5 is not included, but everything beyond that is. All right, so let's look at the next page, which we are going to look at example 6. But let's look at the thing above example 6, which is, okay, now page 211, example 6, we have, now before example 6, let's look at that thing. there's a graph there, so let's look at it for a second. Now the graph of a function, when you look at some graph, okay, the domain is the entire range of x that's in there. It's called the range. And the vertical is the entire height of that thing, wherever it goes, that's called the range. So the domain is the red part, and the range is the green part. However, now if you look at the graph carefully, there's a dot here. It means that the graph stopped right there at the dot. Okay. However, notice there's an arrow there. That means the graph keeps going at this point. So it keeps going down. It doesn't stop, is what that means. So then the domain then is going from this stop point going across. The domain is measuring in the x direction, and it doesn't end. So it goes from here all the way to forever, infinity. Similarly, the range starts here, but it goes down. There's an arrow, means it's not going to stop. So it goes down to infinity. So in this case, negative infinity in the y value. So that is how you read a graph in terms of looking for domain and range. So let's look at this thing. Example 6 on the same page. We're supposed to find the domain and range of this graph. Now in this case, nothing is going to infinity. See, the graph is just a chunk. That is, it started at -3 in that circle there, and got here, and that's it. Okay, it stopped. So the domain is the measurement across. The entire across will be from -3 all the way to +1, not including -3, but does include +1. So that would be the domain. And then the range, yeah, see, that's what it says here, that the domain is, -3, okay, not including, so parentheses, +1 does include, close as a bracket. And similar, next, the range then is, let's look at the range. The range then goes from top to bottom, and it goes, let's see, the range goes from top to bottom, and you notice is it stops here. So the range goes down to -4, but what about the top? Does it get in the top? The height of the y value is at 0. Okay, let me see what your book says. Let's see. It says the range goes from -4 to 0. That, I'm afraid, is not true. But yeah, the reason is because, well, you say, but the domain goes from at -3. The height, there's a circle there, right? Yeah, but get this. Look at what the graph draw. The graph went up and reached y equal to 0, right? It reached the origin. I mean, it reached 0, 0. Therefore, the range does include 0. It doesn't include here, no. But the way it's drawn, it does include there. So the range is is -4 bracket, -4, 0 bracket, not parentheses. Yeah, I'm afraid your book made a mistake here. Well, anyway, but you see why that is, because the range is all possible values of the y value, and the graph, the way it looks, it includes the origin 0, 0 as part of the graph, which means 0 in the y value is part of the range. All right, so that's that. Example 6, then let's next, page 212, let's look at example 7. We have some graph, okay? The book goes in details, but what are we doing here? We are looking for the domain and range of this graph, okay? Is that, just from looking at the graph, so it's a bit of a guess, right? So the domain, it looks like, what is the domain? 19, yeah, that is not that clear. 19, well, whatever. And let's skip example 7, okay, because it's not that clear what it wants. So let's go to the next page, 213, where we look at the bunch of functions that we've seen before and try to determine what their domain and range are. Most of that is quite obvious. For example, the first function is fx equal to c. That is the constant function. Well, the constant function means no matter what your input is, 5 or whatever, the output is always c. Let's say c equal to 1, okay? So if you input 5, the answer is 1. If you input 15, the answer is 1. If you input negative 1,000, and the output is still 1. That is, and you can input whatever you want, and the output is always going to be 1. So the domain is just the domain is the whole real line, okay, minus infinity to infinity, but the range is only C. That's it. And to say that it's only C, you can't draw the bracket like this. That is, your range goes from C to C, which is not much of a range, right? You only got 1 point in there. But strictly speaking, you can say it that way. And so the range is just C. And secondly, let's look at the next function, which is, let's see, where's the function here? Okay, identity function. The function is described at the bottom, all right? So the function, the identity function, it has a name, but it just means x, okay? And y equal to x. So remember, f of x equals to y. So this is the function y equal to x, or f of x equal to x, same thing. So if f of x equal to x, the reason it's called identity is because everything you throw in there, it throws back out the exact same thing. So if your input is 5, the output is just 5. If the input is negative 1,000, the output is still negative 1,000. So then the domain and range are both from minus infinity to infinity, because there's no problem, okay? Anything you throw in, it'll spit out, and everything is good. So next, let's look at the absolute value function. The absolute value function means that you define right here where f of x is equal to the absolute value of x. That means you just kick off the negative sign if your x has one. So if your x is 5, okay, then the absolute value of 5 is just 5. But what if your x is, say, negative 1, the absolute value, then you kick out the negative sign and it becomes 1. And as a result, anything, you can put in anything you want, and it will calculate the absolute value by getting rid of any negative signs that might be there. So the domain is minus infinity to infinity, but the range is always going to be positive, but though it can include 0, of course. And so the domain is minus infinity to infinity, but the range only goes from 0 to infinity. So that's the absolute value function. Next, let's look at the quadratic function, f of x equal to x squared. Now that is is similar to the absolute value function in the sense that you can put anything in there. You know, we can square anything, positive, negative, whatever. So the domain goes from minus infinity to infinity, whereas the range has to be only positive values because anything squared becomes positive. In that sense, similar to the absolute value function. So the range then goes from bracket 0, means 0 included in case you're squaring 0, and it goes all the way to positive infinity. Okay, so then next we have, this is x to the power 3. Now the x to the power 3 looks like this. It's kind of it starts down here, it crosses up to 0, it relaxes, it levels off slightly, to a short level point, and then just continue to crawl up. So then the domain then is, for that, anything you can take the cubic power of anything, of course, multiply stuff by itself 3 times. And then the range then also goes down to infinity. The reason is because if you have a negative number, say minus 2, and you multiply itself 3 times, then negative 2 times negative 2 times negative 2, that becomes negative 8. So then the negative numbers power becomes very, very negative. As a result, the range and the domain are both from negative infinity to infinity for x to the power 3. Now next we are looking at a function called the reciprocal function, is 1 over x. So anything you slap in there, it takes 1 over, and that will calculate stuff. Now for that, the first thing we should notice anytime you see a fraction is the denominator cannot be 0. So x cannot be 0, and x cannot be 0 is the only condition on the domain. That is, the domain is called x not equal to 0. But can be anything else. So the domain then goes from minus infinity to 0, okay, and union 0 to infinity. A shorter way of saying that, x is not 0. A range then is similar because 1 over a number can never be 0. Okay, there isn't a number you can do that you do 1 divided by number somehow will end up being 0. So the range cannot be 0 either, but it can be anything else. And you can solve for anything else and it will be 0. I mean, it will come up with an answer of something. So the range is the same as the domain in that is everything except 0. So y is not 0 is a perfectly acceptable answer for the range. Next, we will consider the 1 over x squared. And that is again, this is similar to the other cases in that x cannot be 0. That's the domain. But the range, being the x is squared, then it tossed out all negative signs. So therefore, the range goes from 0 to positive infinity, 0 not included because, there's no way you can get it to be 0. So 0 is not part of the range. Okay, so next, let's consider what is that square root function. Okay, now the square root function is different from the others in the sense that whatever is under the square root cannot be negative. Okay, and like I said, we're ignoring complex numbers for now. So then all the numbers, everything under the square root sign had better be positive, which means x bigger than 0. It can include 0. We can take the square root of 0. That's fine. So 0 is included. So then the domain is going from 0, including 0, bracket, all the way to positive infinity. The range is the same. It includes 0, and we can it go all the way to positive infinity. And that is for the square root function. So let's look at the next page. Finally, the cubic root function is looks like this, okay? And it looks like the third power, except that it's got knocked over. It's like the y equals x cubed, except you hit it to the side or something. Anyway, so then the cubic root function, now in this case, even though it's a root, being that it's the cubic root, you can take the cubic root of anything, including negative numbers. For example, the cubic root of, say, -8 is -2. Why? Because -2 multiplied by itself 3 times is -8. Okay, so that's why the cubic root has both domain and range as going from -infinity to infinity. So having said that, we are now on page 115. Let's look at example 8. 208. 15. Why did I say 100? Whatever. I don't even know where I got that. Example 8. Okay, on page 215. Let's look at, we're supposed to look at some domain and range of the stuff. Now, so then, let's see. First, we have example A, 2x cubed minus x. Well, that's just some generic function. Everything in there looks good. Okay, no dividing by 0, no taking square root, no nothing. So the domain and range are both going from -infinity to infinity. So please do that as part of your homework. It shouldn't take long. So and then domain and range of f of x. So example 9 I'm looking at, the next one, where f of x is 2 over x plus 1. Now, first you see the fraction. First thing you think of, denominator cannot be 0. So which means x plus 1 cannot be 0. Everything else is good. So if x plus 1 cannot be 0, that means x cannot be -1. Okay, and so that would be the domain, which is x is not equal to -1, or you can write it the long way. Okay, so the domain goes from -infinity to -1, union -1 to infinity. In other words, x is not equal to -1, and then the range then can be everything except 0. Because no amount of x, because if you look at it, no amount of x that you can plug in will spit out 0 as the answer. So then the range is everything except 0. Okay, written it in your book's way is -infinity to 0, parentheses, not including, union, and then 0 again, parentheses, not including, all the way to positive infinity. Okay, next let's look at example 10. The domain and range of that thing, okay, now there's a square root. Now remember the square root has a condition, no negative numbers, at least for now. okay? Because we're ignoring the fact that we know complex numbers and pretend that we don't, or something. And so then the only condition here is that x plus 4 need to be positive or 0. So condition is x plus 4, it had better be bigger than or equal to 0. So we do the inequality, which is the same as equality until you have to multiply or divide some negative number. So let's move that over. That will give us x is bigger than or equal to minus 4. Okay, move it over by changing the sign, same as equalities. So x bigger than or equal to minus 4 is the answer for the domain. Now, another way of saying it is then, of course, like your book, the set notation is bracket, okay, minus 4 comma infinity. So including 4, x can include, negative 4. Then from that point on, it goes all the way bigger to infinity is perfectly good for the domain. Now the range is, being that this is square root, the range can only be positive or 0. So the range goes from 0 to infinity, which is what the book says. See, the range is now goes from 0 to infinity, and that's the graph of the thing. If you were to plot it, it just starts there with a solid dot and then goes on forever. All right, and next we are going to do something called a piecewise function. Now, if a piecewise function is functions that's defined differently for different parts of the equation. Now, to see what that means, let's turn to the next page. All right, let me see. Let's look at this example 11, okay, as an example of a piecewise function. Let's see, where is it? Okay, now we're on page 217, example 11. We have some function, charge. So the cost of attending something museum is for people. The cost of attending some museum is 5N if N is between 0 and 10, or $50 if N is bigger than or equal to 10, which means that N is the number of guys. Okay, so up to 10 guys, then or something, the cost is $5 per person. Any more than 10 guys is capped at $50. So that's the example of a piecewise function, and that's how you write it. And that is example 11. So next, let's look at the next example. Now the next example is something about data transfer. Okay, now the cost of the data transfer, what are we doing here? Find the cost of using 1.5 gigabytes of data and the cost of using 4 gigabytes. Okay, now here is so here's the cost formula. It comes in two sets. That is, between, if the cost is if the gigabytes is below 0 and 2, you follow the top formula, which is just 25. If it's bigger than 2, then it will follow the bottom formula. So that's what's so piecewise about it. The function or the formula comes in two chunks and two pieces. Now, so what are we doing? We first need to figure out what is the cost if we use 1.5 gig. Now, if at 1.5, according to the function description, that's between 0 and 2, so the cost is $25. Now, what if it's 4 gigabytes? If it's 4 gigabytes, then we need to plug it into that formula there, okay? And when g is bigger than 2, which in the case of 4 it is, so let's plug it in here. So that's 25 plus 10 times what? 2? 20? That's $45, should be. And let me check to see if yep, see? So the answer on the next page is $45. Now, next, let's look at problem example 13 on the following page, where we have how to graph some piecewise function. Well, you graph it by drawing each chunk up to that point. So let's graph this example 13. So I have a piecewise function here, and then we're just going to graph it, well, for each part, okay? So here's our function. I'll draw it right here. Now we have x less than or equal to 1 during which is x squared. So let's draw one. Now it's important to draw this by hand instead of using some calculators because you need to get a feel for how to graph things. Once you get a good hang of it, then it's perfectly fine to use a calculator because it's like once you're good at using the fork, let's not practice it all the time. Okay, so anyway, but first let's get to the point that we know how to use the thing. So then for x less than 1 is the function is x squared. So that, well, we'll plot a few points. When x is equal to 1, then of course is plug in 1, that's 1, okay? When x 0, plug in is 0. And then when x is minus 1, is the value is also 1. And that's good enough, okay? So we'll draw this. And we'll draw an arrow here, meaning it keeps going, whatever. And then so from 1 to 2, here's 2. Can you see it? Okay. So from 1 to 2, the value is 3. So this is 1. So we'll go up to 3. And the function from 1 to 2 its value is a set of 3. So we'll draw this. Now, in other words, the function is broken. Okay, there's a solid dot here, and it's bigger than 1, so there's a circle here. So at exactly 1, the function's value is 1, says so right here. Okay, the second it goes past 1, no matter how little bit, the value jumps to 3. Okay, and then it goes all the way to 2, it's still 3, so we draw a solid circle here. And then when it's bigger than 3, bigger than 2, I mean, then the value is going to be x. So when the input is 3, the output is also 3, so it's about right here. What? No, sorry. Let me see. When x is 3, this thing's also, when x is bigger than 2, the value is, let's see, give me a second. So when the function is 2, but slightly bigger than 2, like 2.001, then it becomes the output is also 2.001. So it goes back down here again, but it doesn't include 2 itself. So there's a circle here. And then when x is 3, the value is 3 again. And it doesn't stop here either, okay? It keeps going. So then the function goes like this. And it keeps going. We'll draw an arrow to mean that it keeps going. So here's our piecewise function, very ugly, but that is the idea, okay? And let's look at the next page. Where is it? Yep, that is what the book shows as well. Although, see the piecewise function here? Although the book shows this part going a bit higher, so I can do that. Okay, let's draw it higher, whatever. So then, but that is the right answer. And says that is, what is this? This is example 13, so please do this example carefully as part of your homework because, well, this example is a little more involved and you have to figure out the details of where's the circle, you know, like when is, this part will be the circle and that part will be the solid dot, etc. And things go both sides with drawing arrows. But as long as you pay careful attention and follow the rules, it should come out just fine. So that's example 13. And with that, we have come to the end of this section. Okay, and for homework, please do all the examples, of course. And then on page 220, do problems 9, 13, 17, 21, 29, 35, 37, 41, 45, 51, and 53. And when you're done, I want to talk about some of them. Now that you're done with the homework, let's talk about it. Now, problem 17, I have it written down here. We're supposed to find the domain. Now, remember, if you were to plot this thing in a graph, then f of x is equal to y. Okay, that's just and we just say the function can be called f of x or can be called y. Either way, especially for calculators. But in the meantime, we're just trying to figure out the domain. And as always, when you see a fraction, the domain had better not be 0. That's the only condition. So we'll figure out the domain by figuring out when this thing is, the denominator is 0, and then say it cannot be that. Okay? So the domain says that this is not 0. So let's calculate that. What does that mean? So if this is not 0, we'll factor this to see when does it equal to 0. And And so that would be x. Okay, we're pulling the same trick again and hope that something come out. So that's 22. 22 will be 11 times 2, and that's a positive. Okay, so the positive 11 minus 2, that creates 9. Positive 9, and that should do it. So the domain is any time when x's cannot be 2 and x cannot be negative 11. Because that gives x equal to 2, that gives x equal to negative 11, we'll make this thing 0. Okay, so then if that is the case, then we have to remember that, so negative 11 is not acceptable. Okay, and then 2 over here is not acceptable, but everything else is okay. So we can, so this can be the solution. But if we want to do it the way your book wants to do it, then it would say something like, let's see, what problem is this? 2017, I guess. Yeah, so then the way the book wants to do it is we'll draw this into 3 sections. That section is called, we'll draw it as minus infinity, comma, negative 11, parentheses means 11 not acceptable. And then the second part, okay, that's the part going this from 11 down there. Second part is from minus 11 to 2, parentheses both sides, because those 2 numbers are not acceptable. And continuing, I'll write it down here, or here, continuing, and then 2 comma positive infinity. And that is, so it goes all the way up here. So the answer then comes in 3 sections. Or you can just write that. That's good enough for me, but some teachers might insist that you write it this way just so that you get used to this notation. But they both say the same thing. All right, so that's problem 17. Next, let's look at problem 21, and where we have this situation. Again, we're looking for the domain. Okay, let me write it down. So the next problem, 21, is again, the denominator cannot be 0. Okay, that's one condition. But secondly, being that this is under the square root, f 5 minus x cannot be negative either. So the 2 conditions together means that 5 minus x need to be both bigger than, need to be bigger than 0, 0. It cannot be equal to 0 because it's in the denominator. So this is a strict requirement, which just means that's it. Okay, and put it another way is move the x to the other side because it's negative. Okay, so the other way of saying it is 5 bigger than x, or x is smaller than 5. To do this notation right here, so we have minus infinity to 5. Okay, because that just means x is less than 5. So and not including 5, because including 5 will make the denominator 0, and that is not acceptable. So let's look at 21. Yep, that is the answer in the answer key for problem 21. So next, let's look at problem 35. Flip to the next page. Okay, I found it. What are we doing here? 35, write the domain and range. Okay, we just need to write the domain and range. So that function is, we have some graph here, and the domain and range is, notice the dots, you have 4 dots, okay? So the domain and range of this thing is all limited. And it goes in 2 chunks. That is, first let's consider the domain, one thing at a time. So the domain then for problem 35 goes in 2 chunks. The first chunk is from minus 6 to minus 1/6, including. See, it says right here, it goes down to minus 6, including it, so bracket, and all the way up to negative 1/6. Again, including, okay, that's the negative side. I'm talking about this part here. And then the other side, we'll draw the union circle, union symbol. And then the other side goes from 1/6 all the way up to positive 6. Again, bracket. And that's it. That's the entire domain, okay? And as you notice, the range is exactly the same way. So both domain and range is this thing for this graph because they want it that way, okay? They drew dots, solid dots on both ends of all the ends of the graph. So then this is all the domain and range you're allowed to think of. This is problem 35. Yep, and that is the correct answer. Okay, next let's consider problem 41. So we have, suppose to graph this thing, right? And then write the domain, all right? So first let's graph it. So it says that for x less than 0, the value of the function is at 3. So then anything less than 0 over here, the value stays at a good 3. All the way, but not include 0, okay? So there's a circle there, there's a hole. So, but going back this way, we'll draw an arrow there, it means it's 3 the whole time. Here's the value 3 on the y-axis. And then over that, then bigger than 0, it'll follow the square root of x definition, well, which is good because the square root had better be taking a positive number. Okay, so at 0, it goes to 0, and then it goes up or whatever. So then that is the, and then it keeps going. And so that should be, and at 0, it equal to 0. Okay, so this is a solid dot, and that should be the graph of our piecewise function. And being that it's defined for everything, you know, less than 0 or bigger than or equal to 0, everything's well clearly defined. So then the domain then in this case will be all real numbers, and which is all real numbers is written as negative infinity, infinity. Okay, and so that is so that's problem 41. Next. All right, next we are going to draw this piecewise function where x is, let's see, what's x? X is absolute value for x is less than 2, and then x is, when it's equal to, when it's bigger than or equal to 2, its value is a set value at 1. So let's do that, okay? We'll draw the graph. Let's see, for x, let's do the 1 first, okay, the easy one. So at 2, let's call this 2, the value of x is equal to 1. And it equals to 1 after 2 also, so it's just a level line. Okay, here's 1, let's say. So it's just a level line with a solid dot, and it goes like that forever. All right, so this is the x-axis and the y-axis. Now, so at 2, x just goes, is 1, and more than 2 is still 1. It's just going to be 1 forever. Now, at exactly less than 2, then it becomes the absolute value. Well, let's say at 1 then, okay, at 1 is equal to, at close to 2, let's say 1.999, okay, then it'll be something close to 2 up here because it's the absolute value. So the value starts here, but there's a circle because it doesn't include it. And then at 1, it is going to be equal to 1. So right here, and 0 is 0. Okay, so it follows the absolute value graph. And then when it's negative, then it, if you look at the absolute value graph, it bounces back right here, okay, in the same way, and goes on forever, like this. So that is our graph. And the domain then is all real numbers because everything appears to be defined. Okay, there is no problem with anything. So the domain is all real numbers, and then and the graph looks like that thing. So that is how that comes out. And next, I need to do, that's what, 45. Okay, next I want to do problem 53. Write the domain for the piecewise function. We just have to write the domain, huh? All right, so if we just have to write the domain, that's easy enough, okay? We don't even care about the function, we just need to write the domain. So let's look at what the domain is. The domain says is x less than 1 or x is bigger than 1. And it doesn't, what happens when x is 1? It doesn't say, so that's not in the domain, okay? The function is specified only for x less than 1 or x bigger than 1. It doesn't care about x equal to 1. So the domain then, it goes from minus infinity to what? 1? Yeah. And draw the union sign, okay? And then from 1 to positive infinity. Or another way of saying this, x not equal to 1. And not because it can't, and this function looks fine for x equal to 1, but it doesn't want it to be 1, okay? It says we do not accept 1 in this function, period. It's just an artificial rule, but you better obey it, okay? So so then that is the that is at the end of this section.